And it's easy to verify that this phi is an isomorphism. Then phi is an isomorphism. So next we define now for each I. So we have here the product P. We have a family of semigroups Si here, where I is in the index set I. Now I can define a map that we call the projection map from P to Si. So for each I in I, define pi I from P to Si by let's define this pi I from P to Si, and in there are the maps P. So let's define this pi I of P. It's equivalent IP, because it should be an element of Si and IP belongs to Si. It is an element of Si. We verify that this pi I is ontomorphism, and this ontomorphism is called a projection morphism. We show that pi I is an ontomorphism. So first check its morphism, and onto it's trivial because for each element in Si I can find P such that IP is equal to that Si. That's trivial. So just prove morphism. So let P comma Q belongs to say P, then PQ by I, by definition it's equal to I PQ, and by the definition of the product in P it's IP IQ, and again by definition of pi I it is P pi I Q pi I. So therefore this is an ontomorphism because onto it's trivial. So thus pi I is an ontomorphism. It's an ontomorphism. So next we see that if for any semigroup T, because here P is a semigroup such that for each I and I can define a map pi I from P to Si, and that map is morphism, ontomorphism. So we show that if any semigroup T, if there is any other semigroup T having this property, then I can define a map gamma from T to P such that certain diagram commutes, which I will explain in here. So let's take any semigroup T having the same property. So let T be any semigroup. Let T be any semigroup, and if for each I in I, there is an morphism. There is a morphism, say gamma I from T to Si. There is a morphism from gamma I from T to Si, as there are morphisms from P to Si. Suppose there is any other semigroup other than P, suppose T, so that for each I in I there are morphisms from T to Si. Then there exists a morphism gamma from T to P. There exists a morphism gamma from T to P such that the diagram commutes. So diagram is here. We have map from P to Si, and we have map from T to Si. Then it shows that there should be a map P to Si is pi I and T to Si is gamma I, then we need to show that there exists a morphism gamma from T to P. Gamma from T to P such that the diagram commutes. So diagram commutes means that the composition of gamma and pi I is same as this nu I. So diagram commutes, that is gamma pi I, this composition is same as the gamma I. Okay. So let's define this map. We had to show pi I is given, they are already defined, and now we have another maps gamma I from T to Si. T is a semigroup. They are morphisms. Now we need to show that there should exist a morphism gamma from T to P such that this diagram commutes. This diagram commutes means the composition of gamma with pi I is same as gamma I. So let's define this gamma I. Define this gamma. Define gamma from T to P by gamma of T, where T is in T. So gamma of T, it's an element of P where P is a collection of maps. P is a collection of maps. So it's a map from I to the union. So I is the indexer. So let's write here I. So gamma T is an element of P. It's an element of P. And elements of P are the maps from I to Si. So I will write here T, gamma, then I. Then I will also evaluate this, its value, the value of the map. Gamma T at I. I will define it by it's equal to say it should be an element of Si, because this T gamma is an element of P, and elements of P are the maps from I to union Si, and when I evaluate this map at I, the output should be an element of Si. So I will write here it's equal to T gamma I. Let's define this, because T gamma I, T is a map from gamma I is a map from T to Si. So that means the value of gamma I at T is an element of Si actually. Yeah? It's a map from T to Si. So they are well defined, because both the elements are the elements of same semigroup Si. So let's define this map like this. So we show that we need to show that this gamma is a morphism, and gamma pi I is equal to gamma I. So let's prove it's a morphism. Let's prove that it's morphism. So let's choose any two elements. This first we prove this gamma. Gamma is morphism. So for this we need to choose any two elements of T. Let T1 comma T2 belongs to T. We show that gamma T1 T2 is equal to T1 gamma T2 gamma. Okay, they should be same. T1 T2 of gamma is equal to T1 gamma T2 gamma. Gamma is a map from T to P. So we show that this, and this gamma T1 T2 is again a map from I to union Si, and gamma T1 it's a map from I to union Si. Gamma T2 is a map from I to union Si. So their product is again a map from I to union Si. So both are actually maps. We need to show that these two maps are equal, and maps are equal if they are equal at each point. So let's choose any point. So let I be any element of I, because they are maps on these. Then let's first calculate this one, gamma T1 T2 of I. Evaluated at I, it's equal to, let's evaluate it at I by our definition. Then it's, what's its evaluation at I? It's equal to T gamma I. So here it's equal to T1 T2 gamma I. It's T1 T2 gamma I, but gamma I it's a morphism. It's given it's a morphism, so it's T1 gamma I into T2 gamma I, because gamma I is a morphism. And what's this gamma I T1? By definition, it's value at I T1 with gamma by definition. Here you can see T gamma I is equal to I T gamma. Here it's T1 gamma I, it's equal to I T1 gamma. Okay, so here we have applied the definition. So T1 gamma I, it's equal to I T1 gamma. So it's T gamma I, that's equal to I T gamma. I T gamma. Here it's I T1 gamma, and similarly here it's equal to I T2 then gamma. Okay. Now what's gamma T1 actually? It's an element of P. It's an element of P, and P is a semigroup with respect to the operation is component wise, so it's equal to I of T1 gamma T2 gamma. Okay. So I of T1 T2 gamma is equal to I of T1 gamma T2 gamma for all I and I. So that implies T1 T2 gamma is same as T1 gamma into T2 gamma. So this proves gamma is morphism. Gamma is morphism. Now we need to show that this diagram commutes. Gamma pi I is same as gamma I. Let's prove this. Gamma pi I is same as gamma I. So now we check the value of this at any point. At any point, we'll show that it's equal to gamma I at that point. Okay. So what's gamma pi I? What's gamma pi I? Gamma pi I is a map from T to Si. So I will. It's a map from T to Si, and gamma I it's also a map from T to Si. We will show that they are equal. Therefore, they should be equal at each point of T. So now let T is any point of T. Now let T be any point of T. Then let's calculate this value first. Gamma pi I of T. Then gamma pi I of T. What's this gamma pi I of T? Or you can calculate gamma I of T directly. So what's this pi I of gamma T? It's equal to T gamma of by composition of mappings. It's just a composition here, gamma and pi I. So what's this pi I? It's an element of Si actually, and I defined it like this: pi I of P is equal to IP. That's the definition of pi I. Pi IP is equal to IP. So it's equal to I of T gamma. I of T gamma. I of T gamma. So this is same as I of T gamma. Okay, I can write it as like this. So it is gamma of T, value of gamma at T actually, gamma of T, and that's equal to, here you can see it's equal to I T gamma is equal to T gamma I. It's equal to T gamma I for all T. Let's see. So that means gamma pi I is same as gamma I. That's what we have to prove. Gamma pi I is equal to gamma I. So that's the diagram commutes. That's the diagram commutes. So hence we have seen that if we have a family of semigroups Si, then we have defined P. And then we have shown that there are for each I and I there are morphisms from P to Si, and we have also seen that if there is any other semigroup T such that there are morphisms gamma I from T to Si, then I can find a morphism gamma from T to P such that the diagram commutes. It's T to P. Okay, T to P, P to SI, so either gamma pi I is equal to gamma I. So that's in category theory that any semigroup P having such property is called the product of the semigroups SI. So what's actually product of the semigroup? I will define it in more general setting. So as semigroup say W is called the product of the semigroups SI if there are morphisms, say pi I from W to SI. There are morphisms pi I from W to SI. This W is called the product of semigroups SI if there are morphisms pi I from W to SI. And for any other semigroup T, if there are such morphisms from T to SI, then there should exist a morphism from T to W. Then there should exist a morphism from T to W such that the diagram commutes, such that the composition gamma from T to W and W to SI, this composition gamma pi I should be equal to gamma I. If such thing happens, if this semigroup has this property, that means there are morphisms from semigroup W to SI, and for any semigroup T, if there are morphisms from T to SI, then this should happen. Then there should exist a morphism from T to W, such that the diagram commutes. Then in that case, we can say this W, it is the product of the semigroup SI. And here the semigroup P has such properties because there are morphisms pi I from P to SI, and for any semigroup T, if there are morphisms from T to SI gamma I, then there is a morphism gamma from T to P such that the diagram commutes, such that this equation holds. So such a semigroup is called the product of the semigroups SI in category theory. And we have seen that if the index set I is equal to 1, 2, then the product P of semigroups S1, S2 in category theory is isomorphic to the Cartesian product of the semigroups S1 and S2. And in general, we have seen that if I is the index set, if it is a finite set, say 1, 2 up to n, then the product P in the category theory, in categorical product of the semigroups S1, S2 up to Sn is same as the Cartesian product of the semigroups S1 cross S2 cross up to Sn. So this we have seen. Now next we see that as you all know that given a group G, then for all G in G, we can define a map, or you can say for all A in G, we can define a map FA from G to G by FA of G is equal to AG. And this map is a permutation that we have already done. This map is a permutation. And this set FA, A belongs to G, is a subgroup of the set of all permutations on G. It's a subgroup of this. It's a subgroup of set of all permutations. Let us denote the set of all permutations by SG. So SG is the set of all permutation on G. 1, 1 on 2 maps on G. And this FA, it's 1, 1 on 2 also. It's a permutation. It's a subgroup of G. And we have seen that this G is isomorphic to FAA belongs to G. It's actually a Cayley theorem. So Cayley theorem states that every group G is isomorphic to some permutation group, and that's a permutation group here. Now here we want to prove the same result for semigroups, and we'll see that every semigroup S is isomorphic to some semigroup T, where this T is a sub-semigroup of Tx. Tx is a set of semigroup of all maps on X, not the permutations only. The full transformation semigroup Tx, the set of all mappings from X to X. So we will show that every semigroup S is isomorphic to some transformation semigroup, not the full transformation semigroup. It's a subset of full transformation semigroup. Like here, it's not the full permutation group, it's a subgroup of the permutation group. And here same, T is not the full transformation semigroup. It is a sub semigroup of full transformation semigroup, and we see that S is also morphic to some transformation semigroup. So first we define some basic definitions here. If we know that Tx is a semigroup that we already seen in previous lectures. Tx is a semigroup. It's a semigroup of all maps on X, full transformation semigroup. Any sub-semigroup S of Tx is called a transformation semigroup. Transformation semigroup. Like any subgroup of permutation group, full permutation group is called a permutation group, and same is here. Any sub-semigroup S of full transformation semigroup is called a transformation semigroup. And a morphism, if S is a semigroup, then a morphism phi from S to Tx. If S is a semigroup, then a morphism phi from S to Tx is called the representation of S. By maps. Is called the representation S by maps. Is called the representation of S by maps. So if Tx is semigroup, then any sub-semigroup S of Tx, it's called a transformation semigroup. Now if S is any semigroup, not the sub-semigroup of in general Tx, it's any semigroup, then a morphism phi from the semigroup S to Tx, if there is morphism, if there exists morphism from S to Tx, from the semigroup S to the set of all mappings to the full transformation semigroup, this morphism is called the representation of S by maps, because it maps each element of S onto certain map. Like here, there is a map from phi from G to the permutation group, and this here it's called the representation of the element, representation of G by the maps, by permutation maps. And here we write, here we say that this phi is called the representation of S by maps, because it maps the elements of S onto Tx, where Tx is a set of all